When you walk around on a crutch, it turns out all sorts of other joints start to.
Yeah.
Well, the knee is bad, and it was doing pretty well, but you go on the scooter for a moment and you notice it's getting old. Oh, fantastic. Thank you. Wow. Have the room.
Thank you very much, Barbara.
Thank you.
Hey, don't steal my place in the corner. I want to do a good deed. You can steal that like a tree.
All right.
Was the check?
I got that.
Yeah, I could have said it.
So do you need help with the
I've got a pointer. I've got a
Oh, yes,
clicker.
you're the chairman. You sound like the chairman.
And I hope your silly camera can see me. Can your silly camera see me?
Yes, see that.
Your lovely camera can see me.
Lovely camera. Okay, well, as long as you don't roll around too much.
I won't roll it out. Mostly I want to be able to turn back and forth.
Okay, I think most of your movement is on camera,
Okay, great.
and it might even be recording.
Okay, so first of all, thank you for inviting me and putting up with my infirmities. And it's particularly fun to come as an experimentalist to the INT because most of the stuff you guys talk about I don't understand. And so it's always a challenge to think about what, from the experimental point of view, might be interesting and relevant for you. So I wanted to give you some thoughts about transport, and we can come back to this at the end because you'll tell me whether any of the things that I mentioned actually will teach us about transport, and that's essentially the conversation I wanted to have. Oops.
Just the right button.
Yeah.
No.
Maybe the keynote is.
It's not a keynote, it's PowerPoint.
Okay, can I?
It worked a moment ago.
Yes, it worked a moment ago. Right,
Maybe you just need to click the screen.
You see, you call the camera Celia. Maybe I need to.
If you just click the screen, it might not be.
Oh, it was in Zoom, not the.
Yeah.
Very good. All right.
Very good. Great.
Good. Thanks. So what I wanted to do was to think about what we can learn from measuring transport in quark gluon plasma about trying to measure something about transport in this very interesting cold dense gluon gas. And the question to you is, what should we measure to keep you guys entertained, but also to keep you honest?
Why do you want to do that?
You'll see that's one of the strengths of science, believe it or not, that the experimenters keep the theorists honest and vice versa. So I think it's actually something we do well, so we should keep doing it. Okay, so I want to talk about why is transport important and what tools we might use. And then I want to talk about a few things. Can we measure energy loss in cold dense gluonic medium? Are there medium effects on the soft particles in jets that we might be sensitive to? And medium effects on early branching, which is maybe more likely of interest at an EIC. I'm going to try to focus on EIC a bit, although obviously the data will be from LHC and BRIC. Now, I've noticed in going through slides and sitting through EIC talks that a lot of them give very long lists of experimental observables. And that's kind of natural when you're trying to sell the community on a facility. You have to show how many great things it can do. I don't want to do that in this talk at all. I want to actually focus in on a subset of observables. And of course, I'm going to talk about my favorite stuff, which these days is jets. So, okay, transport. Well, the experimentalist view is a lot simpler than your view. What do we want to know? Well, how does this stuff transport momentum? In quark gluon plasma, we know that the V sub n's are a rather nice tool for measuring the momentum transfer in the momentum transport in the medium. In PA, that's a little bit less clear, and after yesterday's talk, I would say, maybe not. In EA, from what I've seen, and Bjorn can shout at me, but I'm guessing in EA, the visa bends will really be the initial state only, that there will be no sensitivity to anything else. Now, you could tell me the initial state is what's interesting at EIC, but I think you'll see the geometry of the initial state, maybe not the dynamics so much. Now, energy transport is, of course, good fun for people who like to measure jets. The questions that I ask as an experimentalist is how much energy is lost to the medium and where does it end up? And I think from that, I can provide you guys with some data that can then constrain your very sophisticated models of how the transport or calculations of how energy is transported. Another thing that one would ask is how does your medium transport particles? And I thought about this for a while and I concluded that I have no idea what that means in a cold, dense gluon gas. We know, especially if it's saturated with stuff particles in there, it's not clear what happens or how you would tell what happens. It's maybe a place where the theory community can tell us if there are any measurements we should be preparing to make at the EIC. The only thing I could think of is that one could maybe look for effects of the initial state on hadronization by looking as a function of the nucleus size in PA collisions. There's been lots of hand-waving about that, and I think if that's going to be a real scientific program, we need to be a little bit more thoughtful. But having said that, I sit here in front of you with no clue as to how to learn something about it. Okay, now I stole this slide from Bernd Muller's talk at the workshop, and why am I showing you this? Well, there are EIC detector concepts. There's the BEAST at BNL, which you probably heard about from Elke Aschnauer and people working with her. It's a big, all singing, all dancing, very fancy detector. Cool. There's a somewhat smaller EIC detector based on the Babar magnet. And I think what it's got inside is the calorimetry that's being built for SP makes a little smaller, but still lots of upgrades to do wonderful things. At Jefferson Lab, they have an EIC detector based on the Clio magnet. And, you know, if I didn't have these things labeled, and I asked you to please tell me which is which, not only would you have trouble doing it, I would have trouble doing it. And there's a reason for that, and that's that these are all very idealized concepts, and they haven't yet been subjected to typical constraints. Perfect detector, yeah, great. You can design that. You can even build it if you have massive piles of money and lots of time, lots of space in which to put it. Other constraints are the rate of the events. And sociology is also a constraint. I know that sounds really weird, but it's completely true. Everybody has their particular technical strength, and so you put people together to make a collaboration, and that puts some boundary conditions on what you can build. Okay, so compromise happens, and it's going to happen on those detectors. There's not going to be 4. There might be one to begin with, and then one fancier one a little bit later in when the luminosity becomes full luminosity. And they're not going to look like what I just showed you. They're going to make some compromises. And what we need to do, what we need help from you theorists, is to understand the magnitude of the effects we need to measure in order to guide those compromises. And you know, you might think that's obvious, but none of these things that make the boundary conditions actually have physics in them, except maybe the rate. So we also need the physics to guide R&D on the detector technologies, because EIC is far enough away that if we understand that there's some measurements we need to make, and we don't know how to make them yet, there's actually time to develop the technology to do that. And there's a whole community of people who are really good at it and have a lot of fun at that. So that's kind of our side of some of your very fancy computations. Okay, and as I said to Larry, you guys also keep us honest, and this is, I think, a way in which you can keep us honest and make sure that as we design our detector, that we're doing the right thing. Okay, so let's talk about energy loss. List of observables, high PT hadrons and jets, obviously, also gamma jet correlations. So let me start with what's now ancient history. The jet collaboration analyzed the hadron RAA from Rick and from the LHC, and by fitting all of the different data at once, they were able to come up with some constraints on Q hat as a function of temperature. The way they did this was by minimizing the fit parameter, sort of like fitting PDFs. And they found that the data do want a Q hat that decreases with square root of S, and of course in quark-gluon plasma it's large. So what about in PA collisions?
Sorry, does this make any sense? You have the decreases
With temperature?
Units of TQ.
in the units of TQ. So the correlation.
I have running coupling, right?
Yeah.
So that's not.
No, I mean, I get running coupling. Just Q hat is like QS squared.
There's-
Sky the energy.
Oh, yeah.
But the thing what Adrian is saying, if the temperature scales accordingly, then Q hat over TQ would be okay for it to decrease.
So your argument is that, of course, the density has to go up, so the Q hat can't go down. That makes sense. So one of the things I'm going to do is, as we look at things that probably everybody in this room knows well about in quark-gluon plasma, what do we know in PA? Because that's the closest we can come so far to looking at cold dense matter. So here is the high PT hadron RAA. This is for photons. This is for hadrons in lead. And the gray is what you see in PLED. And as you know, we don't see any evidence of energy loss in PLED. As you may or may not have known, that's actually known with pretty good accuracy up to about 10 GeV. So no evidence so far of energy loss in PA collisions. At EIC, well, my guess, if I were going to bet, I'd bet it's going to look like this too, because you don't have a lot of time spent in the medium. But that's actually a question. What's Q hat in cold, dense gluonic matter?
Is that RAE type of an observable, direct observable for EIC to measure energy loss? Because EIC, at least at Jacak, right, you know exactly the energy of your virtual photon, right? So you roughly know the energy of the jet to start from, and then you measure your jet. So you can actually measure the real energy loss, not some energy loss related quantity.
That's certainly true, but then if you vary A, then you vary the size of your medium, and presumably also QS.
No, I mean it's probably an okay observable. I'm just saying it might be better.
Well, okay, that's fair enough. You wouldn't just take the ratio of the hadrons and the ratio of the jets. You know more about the
You don't even need
kinematics.
the proton, right? You can really see the energy loss.
Yeah, you
I
need to.
hope. I don't know.
I think you're telling
No one
me.
ever told me that, so I'm not sure. Maybe.
No, I think what you're telling me is we need to measure the scattered electron,
Which is
part of the
needed to do
plan.
anyway. Yeah,
Right.
the plan. Unless you do that, then
Right. So I guess what you're telling me is we don't need to make a ratio. Now I bet we
I'm
will.
speculating.
Right. I'll bet we'll make a ratio anyway for a technical reason. Namely that a lot of the systematic uncertainties are the same when you run your detector and just change the beam. And so when you make a ratio, you actually can more precisely know what the A dependence is. However, the knowledge of the starting energy has got to help. Interesting point. So actually I should, So I should change this to say at the EIC, what we would probably do is plot as a, take PT slices and plot as a function of the nucleus A. Okay, jet RAA. So I've just grabbed one plot from Atlas, but as we've heard in great detail, the jet RAA is consistent with the picture we get from the hadron RAA and nucleus-nucleus collisions. In p-nucleus collisions, the jet RAA is pretty consistent with 1. This is a ratio of central to peripheral p-lead collisions. You actually very rarely from the LHC see R p-lead, and that's because we don't really know how to count the number of collisions in a p-lead and the number of nucleon-nucleon collisions in a p-lead. There's been all kinds of discussion which, I don't know, you folks might have gone to and slept through as to how do you actually, you can sort the collisions by multiplicity, but it's very difficult to, by the multiplicity, know exactly how many nucleon-nucleon collisions, and if you want to make RAA, you need to do that. So in that respect, I guess what we for sure need to do is to think of a better observable for the EIC. I don't know what that is yet, but it's probably worth some thought. Nevertheless, whatever we're going to see at the EIC is not going to be very big. The effects, of course, you already knew that. Now, how about gamma jet? Well, it turns out that gamma jet is a quite nice tool in AA because the first order, the photon fixes the scattered quark energy and scattered quark momentum, and then you actually can look to see how the medium affects the the opposing jet spectrum. So here what you see is the spectrum, the PT spectrum of jets that recoil against 20 to 30 GeV isolated photons in PP and PLED at the LHC. So this PT range is kind of in the range that we heard from Kyle and from Brian Page that we should be looking at the EIC. The red is the PP spectrum, and blue is the PLED spectrum. And you can see that, within the error bars they're the same. What you can also see is that the error bars are pretty big. You just do a kind of rough estimate. This is within a 25% uncertainty, they're the same. It's obvious that we need to have better precision, not only at the EIC, but also at the LHC. So this is something we need to do better.
So in PLED collisions or PP, you need the gamma. The good thing about the gamma jet is that the recoiling gamma gives you the energy of the initial jet.
Right.
Is that somehow as necessary in DIS, where you can look at events where somehow the gamma, you know the energy of
right.
the,
the
momentum of the gamma star,
right.
and so if you look at just single jet high X, bad X, kind of report, you know the energy
right.
of the initial.
Isn't that what I just said?
Yeah, exactly. That.
But you don't need our EA.
Yeah.
Right.
Because you know the initial energy
right.
exactly, and you can actually measure the energy loss by
right.
measuring.
Yeah.
In fact, you just measure the
actual
energy
loss, right?
Yeah.
Not an observable which
exactly.
is related to energy loss,
right?
But the actual loss.
Yeah.
So the plot will be the actual energy loss as a function of A, but this tells me that this is done with a couple thousand photon jet pairs. This tells me it's just simply not enough, because you can notice that the systematic errors are not particularly bigger than the statistical errors. So this gives you some idea of how we have to do the measurement. Just doing a few thousand isn't gonna do the trick, I don't think. At least not if you're looking for effects that are significantly less than 25%. Yeah, I guess I should. Next time around, I'll try and make some plots that would be EIC type plots about energy loss.
I mean,
I haven't seen them.
So far that problem is I haven't seen this. I mean, I
Well,
think
that's okay, let's make it.
unless somebody saw it, but in all this program, we had some people come and talk about jets in EA, like a digit, for instance.
Right.
And nobody really had the.
That's why you have
rules for it, right?
Right. That's why you have the
So
experimentalists.
maybe I'm like.
I don't know, so there's these people who look at Hermes data and.
No, they don't, they don't think of it this way, right? So, but I think we could make a sort of approximate energy loss prediction.
No,
You know, how well we could do the
measurement.
measurement.
Theory certainly should be able to, I mean, that's what they calculate.
Right, you guys should tell us how big of an effect we're looking for, and then we should make a plot of what
Right,
that.
but then it's wonderful because you don't need to go and calculate our EA, you can just calculate the energy loss.
Right. Good, well, I will,
I seem to remember that in the previous program, there were some
extent.
studies about about that.
So they didn't progress anywhere in the 8 years?
It was very small, but the numbers are probably,
No, QHEAD is very small. of
Right.
course.
but there is also that,
right,
which is the longitude.
so that may be the one to go after.
Yeah, that was, there were some numbers. I don't know how.
Which program was this?
This INT program, EIC.
Oh,
So
the
you're
one
saying
that was
that-
like 4 years ago,
No, it was 8 years.
8 years ago.
The previous,
So probably with better technology now.
Yeah.
And,
right, but no one in this program somehow presented anything like that. So
Yeah. Well, that would be actually useful because then if we can make a simulated plot of the measurement, then we can actually see how well we have to measure and what we have to measure in order to have sensitivity, which I think is important to do now as we're designing the detectors for real.
Excuse me.
Yeah.
So this is a differential number of jets per unit, per one photon.
Right, it's the associated jet. Yeah, this is a new plot. Unless you went to hard probes, you haven't seen this before. I like it because it's from my group.
So if you sum up all this number of jets, then you did actually reduce the error bars somehow compared.
You mean by making just one big PT bin?
Well, just summing over all numbers between PP and PMAT, like because it seems that blue dots are consistently larger and some up, and then
Right.
in terms of total numbers, you might be able to
So one of
correction.
the things that we're working on is to look at some, change the photon bin. If you go to lower PT photons, then you have more pairs. It's technically harder to do because the purity of your isolated photons is lower. So to make this kind of analysis, you have to subtract two biggish numbers. You subtract all photons that have no energy around them from the decay photons that have no apparent energy around them. Decay particles, which aren't necessarily photons. So what happens is a high X, high zero starts to look like a photon.
So within the error bar, there's no difference.
In this range, we have no sensitivity. From 15 to 20, we might be able to. So far, there's no difference, but the error on that is still pretty ugly. So to me, it says we need at least better than 10%, but I think if we make the observable the way added, and I suppose just the jet spectrum bins in jet initial.
yeah, bills of initial energy or something.
Right. But I think in making these things, I think that looking at large A versus small a is what we're going to need to do. And so when we think about running, you can't sit for 6 months on one nucleus. You have to have enough luminosity that you can look at least 2 or 3.
Probably could be implemented. That could be done.
Yeah, as long as the luminosity is high enough. So that also comes in as a constraint on the design of the experiment and the machine. Okay, so in lead, we know that the PT balance between a gamma and a jet is killed by the medium. energy law says that has to be true. This is a plot that I swiped from Dennis Parapolitsa's talk at Hargroves, a month ago. And what you see here is just the ratio of the jet to the photon PT. And you can see here that in peripheral lead, that's in the red, and the blue is PP, you have a peak around 1, as you would expect from QCD Compton scattering. As you go to central collisions, in the lead, that's wiped out. Not surprising if you have a significant energy loss, which we know you do.
Sorry, what is it? On the horizontal axis?
It's basically the PT balance between the photon and the reconstructed jet.
It's the ratio, right?
Yeah,
Yeah.
divided by what?
Right. The photon
PT
divided.
of the photon divided by
Yeah.
the PT of the jet.
Yeah, except I think it's the other way around. I think it's the PT of the jet divided by the PT of the photon.
And that's why it could be above and below.
Right. And there's
Usually when I
probably
see
a
X-
projection in the there too.
Usually X doesn't go above 1.
Yeah. It's not the usual X, right? So, okay. In continuing with this theme that I've set up, what does it look like? Well, actually, let me back up. So, if you look at this, you say, well, all right, this is what I expect. This is for the photons in sort of 60 to 80 GeV. And I'm going to come back to this because if you do this with gamma jet and you do it with dijets, you don't get the same answer. And I mean, it's kind of obvious it's because your denominator is different. So I'll talk about that in a moment. Okay, so what about at EIC? Let's talk about jets at EIC. Here's a slide I stole from Kyle, thank you. And so how do you what are the processes? Well, you can just have an inclusive jet. You can do, as we've been discussing, measure the scattered electron to fix the kinematics, and that's what I'm excited about. And then you can also do photo production, where you select that by a Q-squared cut, as we heard. Okay, so what's interesting? What are we going to learn? Since I'm actually interested in what the gluon distribution looks like, if I want to learn about transport, I'd like to know the gluon density and maybe something about its distribution. So I like the photon gluon fusion channel. You need to measure that. Well, if you want to measure another way, you might learn about the gluons is to look at C-quarks at small x, which we should be able to access, right? So then the jets made in DIS could be pretty interesting. Different, I guess the two processes are going to differ experimentally by which Q-squared you select. We should look at both of them. Is that right?
I think it's an X tool, right? Small x, the left one would dominate.
Yeah, but this one is another, right?
Well, if you want to measure valence quarks,
I mean, if you just measure the lepton, you can also look at small x. We have to see where the jet goes and how many of them there are.
but I think that small x, the rest process dominates because exchanging gluon exchange is dominant with small x. So if you really want to fish out works with small x, that's challenging. I mean, doable.
Well, if you actually can identify jets with heavy flavor,
Okay.
that's how I would go about doing that.
Why is it so hard to longitudinal to get information?
Longitudinal mainly coupled to gluons, yeah.
Yeah, that's right. But you can't go to very small.
I'm just saying that, our standard dipole picture dominates a small x, and if Barbara wants to just couple directly, like on the right, to the quarks, right? The small x that would be suppressed.
I mean, I'm going to get like 12 of them.
Right?
What do you do for
You're measuring, you couple into quarks, right? Because it's small.
Well, you always couple them.
Yeah, so the question is, is it read where you can't do longitudinal smaller?
But I mean, I think it's still going to be the left process which will dominate in FL. of energy move. Right? I mean, you can probably do it. Of course, they will do have small C-core distributions.
Right, it's been done. But I think it would be really interesting to then, select on heavy flavor and look at what's going on in those.
So it may not be structure functions, right? You may look at various, like jet production, we're talking about maybe, you can tag on specific finding state hadrons or jets and C-cores as well.
This tells me something about, then I can look in the kinematics and figure out where I need to be able to find my decay vertex so that I can pick out things. Okay, well let's go back to let's go back to this one, which we all agree is very interesting. And here is a plot that I swiped from Brian Page's talk, because something that wasn't obvious to me, especially in listening to the talks this week that showed the 100, 200 jets at the LHC, that's not what we're going to be dealing with at the EIC. So here you have a plot of the counts per inverse femtobarn for different square root of S and different Q squared twins. And you can see that, not surprisingly, when you go from 141 to 63, the spectrum is steeper, and all the way down to 40, the spectrum is even steeper. That's not surprising. What I want you guys, though, to really look at and notice is it dies off at like 25 jets. And the people at the people in Atlas and CMS would say that's not even a jet. We actually know it is. We know that we've been doing gamma hadron, gamma jet, and lots of things with jets in this range, but these are really wimpy jets. Okay.
The term is mini jets.
No,
Not big jets.
mini jets are below 5, right?
Oh.
That's the way I think. These
Mini wimpy.
Yes. Right. So, I see we're having.
Clean environment in EA. Now you spoke of Thomas Ulrich, for example, did the business study. You can cleanly, using standard jet algorithm, you can reconstruct jets with like 3, 4, 5 GeV.
Sure.
You don't need 25. I mean, because there's not
No, that's right.
pile
It's
of
doable.
junk around. Right.
It's doable. I mean, look, even in P-lead collisions. Look, even in P-lead collisions, jets from 10 to 15 GeV you can reconstruct without any major trouble.
Right.
So you can do it even in PP and P-lead. Maybe next time I'm here, I'll tell you can do it in lead-lead. I don't know how far down we can go,
but here, of course, it's going to be
much messier.
More messy and dirtier, and accuracy is less. I mean, in EA, you can reconstruct angles between dijets and stuff quite accurately because there's just not that much stuff.
Right. So for those of us who come from the heavy ion side, it's like it's going to be a lovely situation.
The problem is going to be a theoretical problem, kind of corrections, more corrections that will follow up there.
You want like these jets.
No, not
It's
necessarily
not the
just saying.
problem. It's
Exactly. I mean, that's the
Yes.
right? It could be interesting to go after.
Well, it's interesting. So in AA, it is a feature because those jets don't, those partons don't travel way out of the medium before they start to fragment. So you can actually see that the medium effects are much bigger for the softer jets. So it's not all bad. It's just that when you make the calculations, keep that in mind. Now, I did a little bit more here, thinking about what are we going to actually get. So I took these rates from Page's plots. I divided them by 2 for the simple reason that he has calculated the rates in a very huge rapidity range. Maybe the detectors will cover all rapidities beautifully, and maybe they won't at the beginning. So I packed off a factor of 2. If you look carefully at the slides that were shown by Bernd Muller and by Rick Yoshida, the goal is that initially they would have data sets that are somewhere of 2 to 10 inverse 2 to 10 inverse femtobarns, integrated luminosity. So if it's 2, and you look at this line here, and so I said, I know that I can do a crappy job of measuring the jet spectra, but measure something, and if I have 1,000 counts. Well, that kind of, even for root S 141, well, that takes me only not even 20 jets. If you can get the 10, the integrated luminosity of 10 inverse femtobarns, then you get out to 20. So keep this in mind when you're doing the calculations. The most of the data is going to be wimpy jets. I think this also tells us that, and this is for EP, so you'll presumably get somewhat higher rate in EA. On the other hand, the way that collider luminosities work, you lose that in the luminosity. So certainly at RIC, those two effects roughly cancel one another. At RIC, the nucleon-nucleon luminosity is roughly constant. And I have to check that the luminosity does go down with larger A at ERIC. I haven't seen a plot of that for JLab EIC. But I mean, if you look at this and you want to measure jets, I would argue that anything less than root S of 90 jets is just not very interesting. You can't measure jets in a region where you gentlemen will be willing to calculate anything. I was pretty struck by that, actually, just looking at the rates in the spectra.
That's based on saying you have to be above 10 GeV?
No, it's based on the last 82 times I showed you jets that were 6 GeV. You guys all said, go away, we can't calculate that.
I didn't say anything.
I have to look at my email files and then I can name names, but yeah.
You're being recorded.
Well, come on, it's the last talk of the entire program, right? So I can be entertaining. It's just sort of a warning of what we're dealing with. Yeah.
So it's like 10 inverse femtobarns that were predicted from last. Like
no, not forever and ever. It's but in the initial first couple of years of running. But that's 10 inverse femtobarns that you would need for one system. And if you want to look as a function of A, it adds up. And of course, all the spin people are going to want to run EP till the cows come home. So we're going to be dealing with wimpy jets, I'm afraid. Yeah, I mean, 15 to 20 kind of assumes we can get inverse femtobarns for a couple of different nuclei, which hopefully is true. The other thing to keep in mind, and that's not so much important for you, but it's important for us. So here's the number of particles in the jet. This is again from Page's talk, I think, that he gave here in week 4. So, when you're looking in this range, 10 to 20 jets, you got 10 particles. This includes neutrals. So you're going to have, I don't know, 6, 7 charged particles. That tells me that the tracking efficiency has to be really good. I can't afford to miss many of them. Not hard to do in these clean systems, but it really means that as we design the tracker, it can't have holes. And we're going to have good calorimetry in order to catch the neutrals, and all of the designs that I showed you have that. So if you have hadronic calorimetry, I think it's not a problem at all to trigger on these jets. If you might be able to do it with electromagnetic calorimetry also. Not sure. Typically at CERN, we trigger on photons. So that actually, I think, is a study that we have to do. And maybe what this is telling us is that all of these fancy detectors that always have a hadronic calorimeter, you really want that. Okay. So I have a homework assignment. I put it as a homework to me, but I think it may be a homework to everyone, which is to really look at the rates for other processes that produce jets. I know, yeah.
But isn't it true that this number depends very much on the energy range you're looking at these particles and also the angles and so on?
So the energy range for this study was everything above 250 MeV. And that, I think, is pretty reasonable given the strength of the magnets in the proposed detectors. You might be able to push it down a little bit and gain a little more, but we know that the soft stuff in the jets is kind of smeary. This uses a jet R of 1. That should be no problem at the EIC. I don't have any concerns about that.
This is hard particles in the jet.
Well, most of them are pretty soft, right? The jet fragmentation function falls pretty quickly at sea, so probably most of them are, you know, for this guy here, right, for 10 GeV jets, they're going to be 1 GeV and below particles. Not a problem to track, it's just that we have to make sure our trackers are very efficient. Tricky to measure the neutral energy in the calorimeter when your zeros are that low. Because if you have a thick enough electromagnetic calorimeter to absorb the energy of a couple GeV photon, then the hadrons going through, the charge hadrons, lead you 300 or 400 MeV there. So it's actually an interesting and slightly tricky, but fortunately the multiplicity is low, so that makes it easier. Okay, let's look inside the jets. This is a picture that I stole from Yassine, and I absolutely love this picture, and I show it all the time because that's how I think about what I would like to measure. I would like to know, do we have these guys? And what happens over here? Okay, so what do you measure? Well, you can measure several things. You can measure the jet fragmentation function, as we heard in Edmund's nice talk, that we come to for this large angle radiation. And we do that, I think there's, the two ways that we do that is by gamma hadron correlations, and I'll show you that in a moment, and by looking at the fragmentation inside jets. We can look at room jet splitting functions, and that would give us some access to those early splittings. And then there are the jet mass, girth, that should be sensitive to rearrangement of jet fragments inside the jet. I think there needs to be some conversation as to what we learn from these kinds of observables at the EIC. I'll tell us some things about that. I think we're just starting to discuss that rather than knowing the answers. Well, let's start with LHC information in lead-lead. So as we know, the jets in lead-lead, the jets have an excess of low Z soft particles, and that those tend to show up at large angles. And of course, the magnitude of these things is what we can use to quantify transport in the quark-gluon plasma by constraining the calculations. But I want to talk a little bit about gamma hadron. It's something you hear a little less about, but it's quite useful because you don't have to reconstruct the whole jet, A. And B, the photon sets the jet energy, and so by just measuring the associated hadron spectrum, you're directly measuring the fragmentation function. These are measurements from RIC, this from Phoenix, this from STAR, and basically what you see is that at low Z or low PT, you do have an excess compared to PP collisions. And of course, at large Z or small c, you have a deficit in Poe-Gold collisions because you have energy loss. So basically, that's exactly the same physics as what we saw in the previous slide at the LHC. Now, the interesting first question we asked when we did these measurements was, well, where does the soft stuff come from? Is it rearrangement inside the jet, or is it soft particles that are kicked up from the medium by the jet going through? And this is the same IAAs from Phoenix for 5 to 7 GeV photons up to 9 to 12 GeV photons. And this was the context in which people told me to go away. And that's where these the soft excess is the largest. The lines are from Xinyan Wang and colleagues' co-LBT calculation, where they include the stuff kicked up by the medium. You can see that that's pretty consistent with the data. And I would argue that over here, the measurement's too crappy to tell you whether the theory is right or wrong. So here's some evidence that at least at the RIC energies, the extra soft stuff is not just those soft branches that Edmund told us about, but also the response of the medium to the energy.
So psi is again the momentum of the jet or photon?
It's basically log 1 over z.
Z is just fragmentation.
You can see the relationship between them here. So high z is log c. It's the log just focuses in on the soft stuff.
Oh, now I see Z. Okay, sorry.
Okay, I think I'm going to skip this because we already talked about it. Okay, so then the obvious question is, what happens in d gold? Well, so the ratio here is the fragmentation function measured in d gold in purple. The blue is pp, and if you make the ratio, the IAA over here, the purple points are what you should look at. And basically you see that d gold looks a lot like pp. So you don't see that medium response in d gold, not too surprising. But once again, it tells us that if you want to do some measurement like this, where instead of measuring the photon, you measure the scattered electron, and so from that you know what energy the jet should have started out with. You have to do a much more precise measurement, and immediately I can tell you you're not going to do that with 1,000 jets. You need to run for longer. Okay, so what about gamma hadron at the LHC? This is again something new which you probably haven't seen unless you were at hard probes. So this is now isolated 12 to 15 GeV photons with a hadron on the away side to try and measure the fragmentation function in PP and lead-lead at the LHC. The PP is red here. The blue is the P-lead. Sorry, I said lead-lead, but it's PP and P-lead. And your eye already tells you they're pretty similar. We measured this as a function of Z, so this is just the opening angle correlation for a couple of Z bits. And yeah, you can see that the hadrons come from the opposing jet, as you'd expect. So if you take the ratio, so you can integrate this, find out how many hadrons came from the jet, and take the ratio of P-lead to PP. Well, first thing you do is you make the fragmentation function. Here again, PP is red, P-lead is blue. So there's the fragmentation functions in PP and P-lead for 12 to 15 jets. And you make the ratio here. And again, you see that P-lead looks a lot like PP. Again, not surprising, but it gives, as we think about designing the next generation of detectors and experiment, it tells us how much better we need to do. We obviously need higher precision. Maybe there's something happening. Maybe not. Within the uncertainties, we can't tell yet. So I think that measuring the jet fragmentation functions at the EIC for different A will be quite interesting. And it probably will be much more precise than here, because here you lose a lot of statistics when you have to disentangle your photons from direct photons from photons from the case. Yeah.
Can you go back to the previous slide? So you have two
two plots for two different ZT.
Yeah,
and
that's just-
that's the ratio of the transverse momenta. So
Right,
is there,
right.
is there some plots where Z is closer to 1?
So
Okay, so here it's
right.
0.7.
the closest that we have is like 0.5, just above 0.5. I do have those plots. I will
Also result per angle.
So those, I don't have them in this talk,
Ah, but
but,
okay.
but if you go to the hard probes talk of Miguel Aratia, they are in his slides there. So you can find them, and then you can play with the integration yourself.
So the left plot integrated to 1. So these are total.
So the way this was made is that, so this is the conditional yield of hadrons per photon. And so then it's integrated from essentially pi over 2 to pi. And then normalized per ZT bin and per unit delta eta. And so it's just counting. No, I don't know how big of an effect to expect at the EIC on the jet fragmentation. And that's a place where I think help from you folks would be very, very good, because that will immediately translate for us into how long we have to run. I don't think we would make the detector any different based on this, but rather depends, it sets the running time required. Now you can compare to the Pythia gamma jet simulation, and you can see that this absolute counting actually is pretty much bang on. Yeah, lots of discussions in the collaboration about this, but we always see that for the higher ZT, the data is somewhat below Pythia. I don't know why. So now I wanted to show this plot from Atlas when thinking about gamma jet. Or thinking about the fragmentation function rather. So this is two different ways that Atlas measured the fragmentation function. This is in lead where there's a big effect. The blue is the gamma tag jets, and you see this large excess here of the soft stuff and the suppression of the higher Z particles. But if you do the same thing and measure inside inclusive jets, you get a quite different shape. And then this was the cause of a lot of discussion. I think it's actually rather obvious. It's because by using a photon to tag the jet energy versus the measured jet energy, you have a quite different denominator of its energy loss. And so that's the shift stuff around. Okay, so at the EIC, we'll do better than gamma jet. I already asked my question, does the cold dense gluon medium modify jets? I don't know. I hope so, to be honest. It's going to be easier because of smaller underlying event. You can use much larger jet radii. You can pin down the kinematics better. But in a way, it's going to be harder. And this, I realize, is just not correct. The kinematic tag is, kinematic tag, I think, goes into the probes. And there's kind of the question of the DIS jets. Is that worth trying to figure out how to do? Maybe. Is there any reason to go after that, or should we focus on just the inclusive jets? Where should I put my time in trying to make
Sorry,
the
what do you mean
EIC
by
pipeline?
DIS jets?
Well, yeah, okay, fair enough. So I was thinking with that at the higher Q square.
Inclusive.
Well,
By inclusive, you mean not even measuring the electron.
I think we have to measure the electron. I think we have to measure the electron, otherwise we don't pin down where we start. Otherwise we're stuck with making an RAA. Okay. Okay, jet substructure. almost done. So, as you guys all know, if you do the jet substructure, what you do is you undo, technically what the experimenters do is they undo the stepwise clustering that we do in the jet finding algorithm. And then you groom the jet to remove the stuff at the softest stuff. As I think we were discussing a little bit the other day, this has got some pros and some cons. The pros are if you want to be able to look at the early splitting, it's great to get rid of the soft stuff so it doesn't confuse you. The cons are that certainly in studying the transport and quark gluon plasma, the soft stuff is what's interesting, or at least it's among the things that's interesting. Those are those large angle splittings. So I don't really know. I mean, maybe at the EIC, the soft stuff won't be so interesting.
But you can still do subtraction without removing. So you don't need to remove the soft stuff instead of the substructure.
Right. And maybe at the EIC you won't need to because it's cleaner.
Right.
One of the big problems is the soft stuff has
less useful actually.
So maybe we just don't want to groom.
Yeah, I don't think because the point of grooming was actually to reduce the soft contamination.
Right.
The other C where you have high, really
right.
high multiplicity here.
Right. I mean, with gamma hadron, you get rid of that stuff by doing a subtraction. You use mixed events, and you pick a photon from one event, a hadron from another, and so you know it has to be the soft background, and you subtract it, but then you get the big error bars because you have a subtraction of two large numbers. So yeah, if we don't have to do the grooming, we don't have to do that subtraction. But maybe 1,000 jets will be a lot better, actually. So we'll simulate that. Okay, couple of things. So momentum sharing of subjets. I think somebody talked about this, right? About ZG. You do the grooming, you throw out the soft stuff so you don't get confused by the underlying event. And then you look and see how often do you have one hard and one soft subjet. So an asymmetric split down here versus two hard subjects, a symmetric split. And this is a plot I stole from Yen-Ji Lee at Hard Probes. And so they, CMS measured that in lead-lead compared to PP, you actually suppress the symmetric splits. I would expect that with energy loss. I think Yassine showed, actually Edmund showed a version of this also. I don't remember, did he reproduce this right? Can you guys reproduce this? Have you tried?
Well, you can if you want to reproduce, but of course.
If you're right.
A lot of people have
Exactly. A lot of people are able to produce this.
I see. So it's not very.
Can you reproduce this and consistently actually understand all of the data at the same time? That was challenging.
Yeah. Good. My gut feeling though is that this will be interesting at the EIC to see if you, as you make your central cold gluonic matter denser and denser, you actually see any effect in this probability of a symmetric split. Is that right? Anybody agree with me? Is my gut in the right place here?
This could be looked at in Proton already.
Funny you should say that. Yes, here's what happens in proton lead. This is now so I tried, I did not find, doesn't mean it doesn't exist, but I did not find a softer jet. These are for 160 to 180 jets, so really zippy jets as compared to the wimpy jets. Here you have 60 to 80, 80 to 100, 100 to 120. So what you see is the same general shape, but if you compare it to Pythia, namely something tuned to PP collisions, you don't see any modification. So
there's no reason to expect that EA will be
right.
Not an expert.
Right. And mean, do we understand why there's no effect in PLED? Should we
Well, you're
try?
looking here at, you see the ZG range. I mean, the smallest ZG is 0.1 out of 6 GBs. You're looking at, the softest subject is 6 GB, and you would expect modifications to start to be somehow sizable when you're at saturation scale. So anything that's really far away from saturation
Sorry,
scale,
but energy loss because of Q-hat scale, which
just
is
saturation.
U squared times R, right? So that is not fundamental scale.
But Q hat is to first approximation, just Q as divided by L, just squared divided by L.
All right, sorry.
So you could really think in terms of QS and forget about Q hat.
Because L is not very big.
Yeah, it's not, yeah, but well, yeah. But you could talk about Q hat, we could also, since the audience is also all X physics, in terms of QS, you can think of comparing the PTs, your subjects to the scale that you can generate by the medium. So if you move away from those medium scales, which means,
I think you just told me you want to see this in PLED for a 20 to 30 JeV jet. Because then ZG of 1 is going to be 2 JeV.
right, I think you will start seeing modifications.
Once we almost.
Almost 1 PLED.
Right. It's a low PT part that will be sensitive.
But I think we probably can do it.
But what's important? You need some theoretical guidance. We need to provide calculations to really provide the size of the effect, so that we can have an idea of how what would be the uncertainty in the measurement that is required to go after that effect.
But I suppose in the meanwhile, we can look into this data set and see if we can do this for 20 to 30.
Just say you go to 20 GB and then you get a 5% effect.
I mean, it gets difficult, right? If you only have 10 particles to begin with, and you groom away a few, and then you split the rest. So I don't know if anybody's tried it for lower than 60 JeV, but I guess that's what we should try in the PLED to get an idea of it. I hadn't actually thought about the QS setting the scale. That makes sense. Okay. All right. Jet mass. So what do we know? Well, your jet mass depends on your grooming. Surprise, 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 right? You throw out if you throw out more of the softish stuff, then your jet mass changes, because the mass has a large sensitivity to the opening angle of the particles in the jet. So, yeah, what do I want to say about that? Well, maybe you have some sensitivity if you don't groom too hard. If you groom really hard, then you flatten the mass distribution. I think that's not surprising. Do we see any difference in PLED from lead-lead? So once again, here are moderate LISA-B jets, 60 to 80 JeV. The blue is lead-lead, so 60 to 80, 80 to 100, 100 to 120, and the jet masses from 0 to 20 JeV. So you can see that if you start here at the highest energy jets, they look pretty similar. You start to see some difference as the jet energy goes down. Here, the PLED is compared to what you expect from PP, using Pythia for that purpose, and see it looks a lot like PP. But based on what you just said, plus the fact that there's some grooming done, maybe that's not too surprising at all. So
these are groomed?
I believe, yes. I believe they're groomed. I have to double check. They are just charged up. It's not good. Okay. Thank you. You know the data from my collaboration better than I do. Oh shit! I am recorded saying that too.
We can leave you.
That's all right. Okay, so I think the same comment though applies that we should go to lower jet energy. Now, I stole a couple more slides from Kyle thinking about measurements of the jet mass. So here, I was really struck that in PP collisions, even with very high energy jets, you have quite a bit of sensitivity to non-perturbative effects. I bet the difference would be really big if you had a 20 jet. And so I then turned to what do you expect for the EIC. Now it's a somewhat different variable, but I see that the difference between next to leading log and also adding the non-perturbative effects, it's not so big. So I guess I have to look at the difference between Pythia and this nice red hatched curve. And that tells me I need to do a really precise measurement if I'm going to have any sensitivity to that difference. On the other hand, if we can finally measure something about hadronization, it's probably worth working hard to do it. But again, even in PP, it's a little bit misleading as to what you would need to be able to do in EIC.
This calculation is for EP, right?
Yes.
Yeah. Ah, good point.
Yeah,
So
maybe
it could be bigger.
power corrections that are enhanced by the site.
But then what do you learn that's different? Do you learn more? Do you have the
Or you
talent?
can access, yeah, you can access the physics that of the structure of the movement.
Okay. So it sounds like this is worth actually trying to go after.
Again, we need calculations. This is for me. I mean, you can go after, measure something, and then you theories come up, say, okay, do something, and then the theoretical uncertainties are much bigger than the research. Or
Well, we know we'll have some results like that, or at least we hope we're going to have some results like that, right? Where we go and measure something, and then the theorists scratch their heads and understand it. But at this point, what's really important is knowing how small the effects that are worth going after are so that we can build the detector that really does it right. Now, of course, these detectors are all singing and all dancing, but just in this subset of questions, I don't know if I'm not sure that it's going to drive the detector design as much as the running time. And certainly the trigger, because we have to be able to measure these things and trigger on those events. Okay, so conclusions. Jets at EIC will be soft like it. PA collisions suggest that jet modifications will be very small. Doesn't mean they're not doable, they're just harder. On the other hand, the measurement's easier, so maybe those cancel. Mapping early splitting as a function of A and EA would be valuable and looks like it's potentially doable. DIS jets, okay, maybe I need to think about it some more. I didn't talk about it, but dijets look like an interesting way to look at the photon structure at EIC. There's a nice paper. You're an expert on that too, right? But there's a nice paper on the web. So I think there's a lot of interesting physics that we can do with jets, and some of it even has to do with transport. Thank you. Well, and I guess as the very last speaker, I want to thank the organizers for doing this very interesting 1-week program that I was here for, but also for the very interesting 7-week program that you folks have put together, and you must be exhausted. So now it's time for everybody to go home and work, right? Yes.
Questions? Comments?
Well, to kind of reiterate this thing that you were announcing, I mean, in fact, I think you should, or maybe a good idea to even consider even wimpy jets, at least if you want to learn something about nuclear modification of the gluon densities, let's say through via jets and dijets and whatnot, then you should probably consider at least going even lower than 10 PPA. If you don't have a huge background, that would be interesting. I mean, if you go beyond 10, or to 15 PT, there's no large initial state modification of the gluon distribution. So you need to look that down.
So there's not only is there no rate, it's much less interesting.
I would like to make a comment here. So the jet community, PP community, they have different culture. They have high energy, then after really precision physics, etc. So it's a different culture. If you tell them, go small PT, I'll tell you, I don't know whether I'm just my calculation.
They'll get to go to.
That's okay. They don't have to.
But the point is that
They don't have to do it, but I don't care what they think. And the point is, I'm not saying
But then the question is whether we are after new physics or just corrections to some physics we already understand. And I think this is the question. And I think that there is some saturation physics can be seen as new physics.
Yeah.
It has not been measured. And Jet can tell you something about that. And for that, we go after the qualitative features or semi-quantitative synchronicity effect and see whether you can.
but you have to go not a PT of 15 GeV, you have to go a PT of basically a few GeV.
And Jet allows you to do that because Jet is most scale tool, so you can really scan much better than
I remember that in EPF era, they went down to 9.
Right.
They claimed that they went down.
I'm trying to make my way back to this plot. So you can kind of read off of here where things go south, right? Obviously, if nature only makes you 4 particles, you're gonna miss one, sort of no matter what. It's gonna be very difficult to say, this is a jet. But in here, you start out with 6 or
But
7.
you have 6, and if you can do it with 6, you can do it with 4. I mean, you just have to put a correction there. I'm just saying.
You may be right. It's going to depend on how on how clean everything else is. And so it's probably pretty clean. On the other hand, if you then want me to make a ZG, if I only have 4 particles to begin with, I'm not sure I know how to decluster those.
I mean, at the LHC, the number of particles you get from a virgin jet is about 20. It's not an order of magnitude. Well, it's an order of magnitude. So the number of particles increases very quickly.
Right. I'm
So if
really
you go up
happy
to
with
20,
10. I'm
you see
happy
it
with 10.
flattens out.
Yeah. Right. 10 is good. 4 makes me nervous.
Yeah.
Now, why is 6 okay?
I mean, so we try to do calculations on what is running on jets, and so about 5 GeV, at least the perturbative QC framework starts right now. That's really, and we can sort of see here, right? There are 4 particles that that's not.
Well, it's substructural tools, they are not.
But certainly
There
substrate.
is no structural
made for.
I mean, the grooming is probably not ideal anyway. Those low quanticities. If you wanted to look like for 1 and 2 pound things, might be better to look at like ends of jettiness or something, because they don't throw out anything.
Yeah, I looked at, I didn't put them in the top.
But I think at least like the perturbative limit is sort of 5 GeV. You know that. Also like the code starting.
Okay, we'll be happy with 5, right?
So 5, I would say.
So that's something that we need to simulate and actually look and see how we can do on those. As far as I know, nobody's done that. At least I haven't seen it.
So we look with LK, like, because essentially pushing those frameworks into the region where it doesn't work, like within simulations and the type of QCD down to 5, it's still sort of okay, but certainly beyond that, there's no. But 5 is like sort of like maybe the goal speaking.
Just understand the result clearly. So is this the average number per jet for a given PT?
I believe,
No,
yes.
every jet you just fill the bins, right? Measure the.
Yes, but
Yeah, I think that's
given
the,
PT, maybe this number could
yeah, I think that's, tell me if this is right. The way I understood this is that the error bar there is the statistical fluctuation in the number of particles.
error bar is the error bar, but
Right, but it's the, I believe that, you know,
Average.
and maybe that's why I'm nervous about 4, right?
It's a simulation, so the error bar is.
But this doesn't look like the error of the mean, this looks like it's actually variant.
Yeah,
Otherwise it would be choppy.
right. It's a statistical uncertainty in measuring. That's the way I use that.
I guess at some point when you go to these 5 GeV, then you start want to look more at leading hadrons and jets.
Yeah, right.
Something that needs to be understood better is how you
I know that story
how
back
you
from
go
Rick.
between the two.
I think this is the answer. The same issues will pop up in hadron because instead of looking at the jet, you can just
Yeah, but
same
some-
advantage. But
But if you measure one hadron, a 5 GeV hadron, you measure a 5 GeV hadron, you don't need to worry about whether you missed 25% of the hadron. If you're a 4-particle jet, you miss one of the particles you're missing.
This is like year 1 of Rick. It's how we ended up, how we started with the
This is how it
hadron
started.
arrays. Yeah. But I mean, maybe what you gentlemen are saying is that the best observable for these wimpy jets is the fragmentation function, right? Because if you have an effect in the first splitting and you only have 5 or 6 particles, then you should see some change in the slope of the fragmentation function as you change A. Does that make sense?
yes, and fragmentation. I mean, fragmentation of course scans. It's similar to the
Yeah, so I don't know, is the fragmentation function something which contains the physics you're interested in? Or is the fragmentation function something you measure so that you can use this measurement then to measure measure leading particles and transform that into a jet spectrum? Assuming, but if you do that, then you have to assume that the fragmentation function is independent.
Well, I mean, these are fragmentation functions. These are ratios of P, lead to PP, but those have more information than just measure it because you can.
You see, I mean, jet physics in heavy ion conditions of the LHC is really messy in the sense that it's a violent environment. For the theoretical calculations, if you can, if there's some kind of sweet spot where you don't go too low in PT, say, not below 5 GeV, and you can provide, calculations and look for observables. This is another thing that we need to come up with. I mean, this is really, we are really in early stages of jets in EIC, so we need to, theorists need to work hard to really make the case for some observables that mean, say, for instance, do we need 120 GeV advance or 90s? I mean, you see, this type of decisions need to be made and be supported also by the steering communities.
Right. Well, let's actually go back to this plot. So I would argue that we're really unhappy with 40 no matter what, because then all you have are these things where there's only 5 or 6 particles. So you don't have a hook to hang your hat on. Maybe 63. If you run for longer, maybe that's enough. But I think if you told me that this is the spectra I'm going to get, I would say I'm going to do something.
So is it a
else.
matter of cost going from OG, or is it just?
It's the accelerator design. I believe it's the case that both competing designs now plan to get to close to 100. That wasn't the case 6 months ago, but I think the National Academy report says you need to have the full range in the US.
But of course, higher energy costs more for reservoir. So.
Well, that's right. You need stronger magnetic fields.
Yeah, but how much more? I mean, say you double the energy.
We're not going to discuss money here.
Right. I don't know the answer to that. I know that the JLab people in Yoshida's talk the week before, he said, oh yeah, we can get the higher root S, we just double the number of Tesla in each magnet. And it's probably doable because I think the magnets are not harder than what they're doing for the LHC upgrade, but I don't know what the implication funding-wise is. I don't know if it's only double the money.
All right, if there's no further questions, let's close the session.